first problem is the wedge-like fin. The problem says you have a fin which is in the shape of a wedge. It has a base height of b0, and its width goes to 0 at a distance L, and its width is W. The system is cooled by a fluid at a temperature Tf. The fluid has heat transfer coefficient H, and the wall is kept at a temperature Twall, Tw, and my x-axis is to the right, this way. Let's call it x is equal to 0. Let's call this x is equal to L. The problem asks us to derive the governing differential equations and list all the boundary conditions. And we are not supposed to solve the governing differential equation, but we should actually come up with the equation that actually tells us what the T temperature should be. And it says that T of the solid can be assumed as a function of x only. Okay. So probably the bio number is much smaller than 1. That's the reason. We should actually write down the heat balance. We need to pick up a shell with a width of delta x. And let's assume that the height is b of x, and b of x, just a side note, can be written as a linear function of x, because you can see it from the geometry, it decreases linearly with x. b0 times 1 minus x over L. Let's try this one. If x is equal to 0, you get b0. That's correct. If x is equal to L, you get 0. Okay, that makes sense. Okay, so you can actually model the bx as a linear function of x. Now we can actually do the shell balance. Whatever goes in minus whatever goes out plus generation is equal to accumulation. And assume steady state. Let's assume steady state. The accumulation is 0, generation is 0. No mention of generation. And the in is qx times the area perpendicular to the heat flux, which is Ex times W, and calculated at x, minus what's going out is basically the conduction and also heat convection. The conduction term going out is Qx E of x W at x plus delta x, minus the convective term is H times the area is basically the perimeter W plus Ex times 2. So H times perimeter times delta x gives you the H times area times T of x minus T of f. And that's all in and out. That's equal to 0. Let's simplify this equation by dividing by W and delta x, and noting that yeah, we can plug in the px later. W is not a function of x, so it can cancel. Delta x cancel here, and this term on the left is negative of the derivative with respect to x. of whatever inside. Qx dx is equal to h times, instead of px, 2 times w plus bx divided by w, tx minus tf. Okay. Now, using Fourier's law, this gives minus d over dx minus k dt x over dx b of x is equal to 2h w plus b x divided by w t of x minus tf. Okay, and after simplifications, we get d over dx d of x dt x over dx is equal to 2h w plus bx over k w tx minus tf. So almost all. You can plug in the bx now, and h w plus p of x divided by kw tx minus tf. Dividing both sides by v0, you get d over dx 1 minus x over L dt of x divided by dx is equal to 2h w plus p of x divided by kw v0 tx minus tf. There you go. So this is your governing differential equation, which is being asked in the problem, and we need to list the boundary conditions. It's not an easy task to solve this equation, so we're just going to leave it there, as the problem statement suggests. And let's list all the boundary conditions. Boundary condition 1, at x is equal to 0, the temperature is equal to Tw. And the second boundary condition is at the tip of the wedge here, you can assume that there is no more heat conduction to the right, because it's the end of the conduction zone. So from the Fourier's law, you can get at x is equal to L, Q of Qx is equal to 0, and that's equal to minus k dt over dx at x is equal to L. So from here, at x is equal to L, you get dt over dx 0. Okay, so these are the two boundary conditions which are being asked in the problem. There you go. So that's all. Any questions so far? No.
Where did you get the B of 0 equation? The B of X equation, I mean.
Yeah, it's from geometry. You can see. So let's write it from geometry. So let me be more specific. Imagine you have this triangle, right? Oops. B0, correct? And you have this B at any x. And imagine that this much is x, correct? And this much is L. From the similarities of triangles, right? The green triangle is similar to the purple triangle. Oops. So, and are similar triangles. Thus, B of x belongs to the green triangle divided by B0 is equal to, the green triangle has L minus x divided by, the purple triangle has L. Right? Now this should make sense. Correct?
Correct, yeah.
And after rearrangement, you get B of x is B0. You multiply B0, like both sides by B0. And if you take, so let's go step by step. And then from here, B0, if you divide by L, you get 1 minus x over L, right? So you basically divide this by L and divide this by L. That's how you get this. And we can actually put it in a bubble. And make it student friendly. Okay, good. Any other questions? No? Okay. So if you don't have any questions, let me start to solve the second problem. We have a hot wire anemometer. Basically, we have a fine wire like this, okay, made of platinum, okay, which is heated electrically while exposed to a flowing fluid. And the flowing fluid has heat transfer coefficient H, let's assume. Okay, so this is heated electrically, so there's a heat generation R dot, which is known to be 1 over KE times I over A squared, correct? KE is the electrical conductivity, if you remember this formula. And the wire temperature is going to be a function of fluid temperature, right? Because your fluid, which is given as, is it given here? Must be TF, I guess. So the fluid temperature is at TL too. It's given the problem, and the two ends are also kept at TL. So the idea is that the temperature of the wire is just going to be a function of the fluid temperature and also the flow conditions. Like if you flow a faster air, the heat transfer coefficient H is going to increase, so you can have a different temperature profile. So you can actually get an idea about how fast the air is moving if you can actually probe the temperature of the wire. Okay. The ends are kept at temperature TL. Right? Okay. So the wire has a diameter D. And a length 2L. And we're going to call the middle of the wire as Z is equal to 0. And this is going to be Z is equal to plus L. And this is going to be equal to Z is equal to minus L. That's my schematic. And the electric is being flowed at electric current density of I. Basically, the nomenclature, so the I in the problem statement, what is given as I corresponds to I over A in our earlier notation. So basically, we can model the heat generation rate as 1 over KE times I squared. That the notation in problem statement. So you should actually make yourself comfortable. You should actually get used to the fact that you can go from one notation to another as long as you know the units of the symbols, what is meant with them. So, and you can also do a dimensional analysis to understand why this R dot is 1 over KE times I squared for this problem. Okay. Okay, so part A. Derive an equation governing the steady state temperature distribution in the wire, assuming that T depends on Z alone. Assume T is a function of Z only. And clearly state the boundary conditions. Further assume uniform thermal K and electrical conductivity is KE and uniform heat transfer coefficient H. All temperature independent. Okay, so good. So far, so good. So let's do a shell balance. Balance would give and you're also losing some heat. Q convection. Okay. So there's a generation inside. Okay, so we're going to write down oops, in minus out plus generation is equal to accumulation. It's a steady state problem, accumulation 0. There is generation, there is in, there is out. In is just Qx at x times cross-sectional area. Not a function of x. I can keep it in the parentheses or maybe take it out of the parentheses, doesn't matter for this problem. Minus what's getting out, what the conduction is, Qxa at x plus delta x. And note that I'm actually doing the Qx's in this direction instead of this direction. It's because my positive z direction is towards the right. So that's why that actually declares which way actually I should place the Q-axis. And plus, oops, sorry, there's one more out. That's equal to h times the convection term. H times area is basically the perimeter of this shell times the delta x. It's basically the area of this thing. So this area I'm talking about, and it's basically this perimeter times the thickness, and it gives you this area of this rolled paper. Okay. Okay. Which is the perimeter is basically pi d, right? Delta x times the differences in the temperature, T minus Tf. Or basically the fluid temperature is given as TL. Okay. That's equal to, we also have a generation plus volumetric generation rate times the volume of the shell. The volume of the shell is the area of the cross-sectional area times the thickness. That's equal to 0. Okay. And let's divide all sides by a times delta x. Cancel the a's. Cancel the delta x's, fortunately. And you take the limit as delta x goes to 0 and take to find minus d over dx q of x minus h times perimeter pi d over a t minus tf plus, here the a's also cancel, r dot is equal to 0. And now we're going to use the Fourier's law of heat conduction to get k times d squared t over dx squared minus h pi d over a t minus tf plus r dot. And instead of a, this term, it's the area, cross-sectional area, right? You can write it as pi d squared over 4. Right, the area of a circle. And after simplifications, canceling one of the d's, you get 4h over d there. And let's divide all sides by k. You get d squared t over dx squared minus 4h over kd t minus tf plus fancy r dot is equal to 0. Okay, I guess that's the equation we get.
It's supposed to be r over k, the fancy r over k.
Yeah, exactly. You're good. Yeah, correct. Yeah. There you go. Okay, good. And you can check the units to see, like, all the terms have the units of temperature divided by length, or Kelvin divided by meters. Okay, you can check the units to make sure you're not doing something wrong. Okay, good. And you can actually plug in the value of the r dot as well if you like. So d squared t over dx squared 4h over kd t minus tf. I mean, and also the tfs, we can actually replace them by tls, right? We said that here at this point. So let's make them tl to be consistent along. Plus, instead of fancy r dots, we're gonna write 1 over ke times I squared. Here, I is not current, but it's the current density. Okay. So that's our differential equation. We need to write down the boundary conditions as well. At x, these are all z, right? So this must be z direction. But that's okay. So let's make them x. How about that? There's not going to be any problem in changing the z to x, right? It's just the name we give. Okay, cool. There you go. At x is equal to minus L, the temperature is equal to TL. At x is equal to plus L, temperature is equal to TL. Do I have any other boundary conditions? I guess no. And I don't need any more because, I mean, I just need 2 because this is 2-dimensional, sorry, second order ordinary differential equation. So I only need 2 boundary conditions. Any boundary condition more than 2 will be redundant. Okay, now that's part B. Oh, that was part A. Now let's do part B. What does it say? Non-dimensionalize the equation. To convert it to a form d squared y over dx squared plus ay is equal to b. And solve the equation by applying the relevant boundary conditions. and solve the equation. So that's our task. What are we going to do? Any suggestion for the non-dimensionalization? Well, non-dimensionalization of the position is pretty straightforward. You just choose a characteristic position or length, which is basically easy to find from the schematics. It's just the L. Okay. There is another actually length scale, which is the diameter of the wire, but it's not relevant to. It's not a good candidate for a characteristic length. The reason is because I'm talking about the heat transfer along the x direction, and I know that the temperature only varies along the x direction. So my characteristic length must correspond to a length along that direction, not the length along this direction. If I were to compare the conduction to the convective heat transfer along this direction, then the D might be a good candidate, but it's not what I'm doing right now. I just want to normalize or rescale this minus L plus L direction. Okay, so my characteristic length is L. Thus, I should define a new positional variable, x over L. I need to normalize the x by L, and I need to call it something like, for example, psi. You can choose any Greek letter you like. Okay, and the reason why we're using Greek letter is just to differentiate between the non-dimensional numbers and the dimensional numbers, dimensional quantities versus non-dimensional quantities. Generally, in transport processes, we are accustomed to use Greek symbols to denote non-dimensional quantities. Okay. For the temperature, characteristic temperatures are only TL, right? If I had TF different than TL, I would actually list TL and TF. I would be definitely using the TL and TF at the same time. So, but this time I only have TL, so you can actually normalize T by TL, right? Okay. But there is one more thing you can do here. Have a look at this equation. Have a look at this equation, please. You see that there is T minus TL appearing there, and it might be a good idea to have the T minus TL in your expression so that actually you can have one term here instead of like T minus TL. Instead of a difference, you would get some quantity itself. So instead of T in the numerator, let's have T minus TL in the numerator. And that's not a problem because that's still a non-dimensional number. Okay. If I had TL and TF differently, I would be choosing something like T minus TL divided by TF minus TL. Or maybe T minus TF divided by TL minus TF, depending on whether I have the T minus TL or T minus TF in my equation. But since that's not the case, I'm not using those. Okay, so that's the procedure how you can actually non-dimensionalize the temperature. And let's call this theta. Okay. So let's start to actually come up with the non-dimensional version of this thing. So what we're going to do is basically we're going to write down d squared theta over d psi squared instead of d squared t over dx squared, we're going to relate this to d squared t over dx squared. And here's how we can do it. D squared theta over d psi squared is equal to d over d psi, d over d psi, and instead of t or theta, we're going to write down t minus tl divided by tl. And instead of d psi, we're going to write down, since psi is x over L, it's going to be d x over L. Again, similarly, here. Okay. And from here, these L's, you can make it upside down and put it here. That's going to be L squared. And the TL, this TL, can come out of this derivative because it's a constant. So L squared over TL, d over dx, d over dx, t minus TL, but since the derivative of a constant is 0, you can just get rid of that, and you get L squared over TL, d squared t over dx squared. Or you can write the other way around, d squared t over dx squared is equal to TL over L squared times d squared theta over d psi squared. Okay. Now I can actually place this in this equation. Right? And also let me get this thing done as well. For h over kd. T minus TL is equal to basically, you can divide and multiply by TL to make it 4h TL divided by kd theta. Okay. And also note that this thing must be dimensionless. No, sorry, that thing must not be dimensionless. So we're going to see how it's going to convert. Okay, so that's the second one. So we're going to replace the left-hand side by the right-hand side. We're going to plug this in this equation. Okay, and your equation is going to look like the following. Oops. You get TL over L squared d squared theta over d psi squared minus 4HTL over KD, I guess. Theta plus I squared KEK plus I squared over KEK is equal to 0. So let's make every term dimensionless. So let's get rid of this thing so that this becomes dimensionless and each and every term will be dimensionless. So let's divide all sides, all terms, all terms by TL over L squared. So you get d squared theta over d psi squared minus L squared 4H divided by KD theta plus L squared I squared over KEK TL is equal to 0. Now, this is dimensionless. This is dimensionless. So, since this is dimensionless, this entire thing must be dimensionless. So, since this is dimensionless, this is also dimensionless. Similarly, this entire thing is dimensionless. You can check the non-dimensionality of those constants too. So, let's call this, for example, H. Okay, like a dimensionless number. And this one, another dimensionless number which corresponds to the heat generation rate. Let's call it J. Okay. So what we have basically is d squared theta over d psi squared minus H theta is equal to minus J. So we got this non-dimensional equation. So we did part of the part B. And our boundary conditions becomes at psi is equal to +1 or -1. Theta becomes equal to TL minus TL over TL, which is equal to 0, right? Okay. So this is both the first and the second boundary condition. Let's call it boundary conditions. Okay. So we non-dimensionalize both the governing differential equation and also the boundary conditions. What kind of a differential equation is this? It's second order, non-homogeneous. Ordinary differential equation, right? So you can actually write down the solution as a sum of a complementary function and a particular solution or particular function. So it means the following. You can actually write down the solution to the homogeneous counterpart of the same equation plus any particular solution that any particular solution that solves this equation. Okay, and the complementary solution, theta complementary solution, is the solution to the inhomogeneous counterpart of this equation. Let's write it down. Homogeneous counterpart of this equation is the following. You just get rid of the j, which actually makes the inhomogeneity, right? D squared theta over d psi squared is equal to h theta, right? So you need to find the solution for this. So this called the solution theta complementary solution. Okay. And as you know, the solution to this equation, since h is positive, is equal to C1 times cosine hyperbolic square root of h psi plus C2 sine hyperbolic square root of h psi. Okay. Because these are exponential, and any linear combination of exponential and exponential minus can be written as the combination of cosine and sine hyperbolics. And theta particular solution is, we just come up with any solution that solves this. As you can see here, if you actually plug in a constant number here, the derivatives are going to be 0. And this constant is going to be equal to this constant. So the constant you can actually plug in to make it correct for just one case would be j over h. So if you plug in j over h here, you see that this will be equal to this, and then this is going to be 0. So j over h must satisfy this equation as well. A particular solution that satisfies. From observations, we get j over h, a constant number. Thus, the theta can be written as the sum of the theta cs plus theta ps. Thus, we get C1 sine hyperbolic square root of h psi plus C2 sine hyperbolic square root of h psi plus j over h. Okay, and I'm going to have two boundary conditions to solve for C1 and C2. Okay. So, as you know, the solution must be symmetric about psi is equal to 0. You can say that this must be cosine hyperbolic type of function, so C2 must be 0. Or in other words, so what we can do is basically, you can write down the boundary conditions if you like. You would say that 0, theta will be 0 at psi is equal to plus and minus 1. So you would get C1 cosine hyperbolic square root of h plus C2 sine hyperbolic square root of h plus j over h. And then 0 is equal to C1 cosine hyperbolic minus square root of h But the cosine hyperbolic is an even function, so you can write it as just cosine hyperbolic square root of h. And the sine hyperbolic is an odd function, so you can write it minus c2 sine hyperbolic square root of h plus j over h, right? And if you subtract the 2, right, you cancel these, and you get 2 c2 sine hyperbolic square root of h is equal to 0. From here, you get c2 is equal to 0. Or you can, as I said, you can use the argument that the function must be symmetric with respect to psi, so that it must be like a cosine hyperbolic type function, so c2 must be 0. So that's another way of finding it. But you can use the boundary conditions directly. So your function theta becomes equal to c1 cosine hyperbolic square root of h psi plus j over h. Let's use one of the boundary conditions again to find the c1. At psi is equal to 1, theta is 0, and this gives us the c1. c1 is equal to minus j over h times cosine hyperbolic square root of h. So if we finish, then we find that theta must be equal to minus j over h in parentheses cosine hyperbolic square root of h psi divided by cosine hyperbolic square root of h minus 1. Okay. That's the solution. Any questions so far? No? We're running out of time. We're almost done, but let me just, for the sake of completeness, let me check the entire problem. In part C, compute the current in amperes required to heat a platinum wire to a midpoint temperature of 50 centigrade under the following conditions. So this might be a good exercise for you to do. So solve part C as an exercise. Okay, and let me know if you have any problem. So you will be finding I, the value of I, from the given data.